Thank you. Screen.
Yes, doctor.
Okay, thanks. So we proceed with integration. So we have EI, V comma 1, 2, 3, 4 minus F delta X minus A. And we go on. Integrate 1. So we said EI, V comma 1, 2, 3. See, you integrate the delta and you obtain the step. And you include a constant. Okay. So this constant is equal to EI sub C V comma 1, 2, 3, and 0. And also minus the integral of this at 0. So all of this evaluated at 0 is this. And this is the this function evaluated at 0. Now, if this is equal to 0 at 0, so that is this is 0 at 0, then A is exactly this one here. And you can recognize that this is the minus the shear force at 0. In some cases, you have this as boundary condition, and that will help you to calculate those constants. Okay, we go on. EI sub C V comma XX is equal to minus F, and here we have the ramp function. This is the ramp function, AX and plus another constant. And then we integrate one more time. X minus A squared over 2. Step function, X minus A plus AX squared over 2 plus B. Okay, because this constant C, okay, this constant C is equal to EI comma X at 0, then minus the integral, this term here, okay, evaluated at 0. Now you can see here that if I evaluate all of this at 0, so the step function is 0, I have X, so everything, all of this is 0. That means that C, in this case, is EI V comma X at 0. But this is a boundary condition. So immediately you see that this is equal to 0. Okay? Since this is equal to 0 at X equal to 0, this is equal to 0, and this is equal. Since all of this is correct, then C is equal to E actually C X at 0. And since this is equal to 0, then C is equal to 0. This is something that if we recognize, we can save some time. We can go on. One more time and say that E actually C V of X, this is a function that I'm trying to determine, minus F X minus A cubed 6 step A, and then we have plus AX cubed over 6 plus BX and plus D. We know that C is already 0. And again, this, in this case, is equal to EI V at 0. Only in this case, since all of this term is equal to 0 at x equal to 0. So if this disappears, evaluating at 0, then this is equal to 0, and this, of course. So we have to determine two constants, A and B. And for that, we have two boundary conditions, displacement and rotation at L.
Teacher, I have a concern about the negative sign of V of X, the shear force, because when you replace the boundary condition at points equal to 0, you have a negative.
But Ms. Santos, I think it's Ms. Santos, right?
Yeah.
We still have not any shear force determined.
No, but when you replace at the boundary condition at a position equal to 0, you have A. And when you replace that, you put as a negative B of 0 or as positive B of 0.
Let's suppose that I integrate x dx from 0 to
X.
No. Let's do this. Okay. The problem here is sometimes you get confused. Let me. What I'm going to do here is just something from your calculus. Okay. So I'm going to integrate 0 to zeta x dx. And this is equal to what? X squared over 2. 0 to zeta. And this is equal to 1/2 zeta squared minus this negative is this negative. So what I do is I integrate this term and evaluate at 0 and an x. See, evaluated at 0 at x is this one. Evaluated at 0 is this one, but with negative sign. The same thing on the left-hand side, but I move it to the right, and that's why I put it as positive. Ms. Santos? This is just okay, this is
un poco confuso. But in the last slide, you put B equal to 0, B at 0 equal to P. But when you replace at minus I, B at 0 equal to P. This
is including the negative sign. This is B at 0.
Yeah.
We said that mz is equal to EI sub C V comma XX. Okay, and also we said that B and C dx is equal to what?
EI.
It's minus V of X. That's why we can say that V of X is equal to minus EI sub C V comma 1, 2, 3. So what I'm saying is that the V at 0 is equal to P, but V at 0 is equal to minus all of this.
I got it. Thank you.
No problem. No problem. I'm glad I could help. So let's find the two boundary conditions. So we said, okay, we have EI sub C E comma X at L is equal to minus F X minus A L minus A squared over 2 and the step function, which is 1 plus A L squared over 2 plus BL, and that has to be equal to 0. Is that correct? Yeah. So that's one boundary condition. And the last one is I sub C V of L is equal to minus F L minus A cubed over 6 plus A L cubed over 6 plus B L squared. It has to be equal to 0. Those are conditions. Are you with me, people? So I have two unknowns, A and B, and two equations. So we could solve it. And you could do the details. And I'm going to give you my
Doctor,
what I obtained. Yeah.
In the last one, you don't want to add the denominator
2 over 2.
2 over 2BL squared over 2.
Oh, yeah, I'm missing here. Thank you. Thank you. So A is going to be what is going to be 6 F L minus A square over L square and 1/6 cos A over 3L. A little bit differently, we can say that this is 6F, and this L, we could put it inside, so it's going to be 1 minus A over L, and then square. 1/6 plus A, 3L. This is A. Everybody with me? Now,
Yes, doctor.
yeah, do you have a question?
Uh,
Okay, so minus EI sub C V comma 1, 2, 3 of X is equal to V of X, right? So if we go from here, we could evaluate. So minus V of X, okay, change signs here, so it's equal to minus F step function X minus A plus A. So it's the first integration. Yeah. So minus V at 0 is equal to this is 0, the step function at 0 is 0, and plus A. So A is this one. It's all of this. And now this is the, so the shear force is equal to minus B minus A. And now we interpret this. So on the left-hand side, we have the support here, and we have a reaction here that we do not know. We may cut very close to the end. This is X. And here, I put the shear force. Okay. So we know that they have to be in the same direction. So correct. So R sub A is equal to minus B at 0. So I have one negative here and one negative here. Okay. So that means that this is equal to 6F 1 minus A over L squared 1/6 plus A over 3L. This term here is positive or negative, people? This term here is positive or negative?
It's positive.
It's gonna be positive.
Yeah, it's positive. So does it make sense that this be positive?
Yes.
Make sense? Remember, what is RA? RA is an external force acting on the system. So the external forces, remember, they are, the sign convention for the external forces is this one. Y is positive upward. So if this is positive, that's what we were expecting, because it's pointing in the correct direction. Okay, now, what would happen, people, what would happen? Let me go back. What would happen if I apply the force on the left end? Let's ask somebody, Mr. Chin Chin, what would you expect if I would apply the force on the left end?
We need to consider the F in the end.
Could you please speak louder because I cannot hear you. Go on.
We need to consider this concentrate force in the left end.
Yeah, but can you see the figure?
Yes.
Okay, if you apply the force on the left end, what would you expect for the reaction?
Action outward.
More than that. Mr. Paredes, Daniel Paredes, if you apply the force F on the left end, what would you expect?
Good morning, doctor. If we have force on the left end, we have considered in the boundary conditions.
Oh, no. Explain it myself.
The reaction may will be equal to the force.
Yes. If I have something like this, and I apply the force here, then the reaction will be equal to the force. What would be the condition for this case to be considered? What would be the condition for this case? How much would A value?
0. So close 0.
Exactly. If you replace here, 0 here, say this is going to be 1/6, this is going to be 1, so RA would be 6F times 1 times 1/6. Makes sense? Question, what would be RA if you apply the force on the right end?
0.
In that case, what the value of A would be?
L.
So if you put it here, RA would be 6F, 1 minus 1, and that's 0. Make sense? Yes. So if you apply the force here, this support will take all this force, and the other end will take nothing. Questions, people? Questions? Questions? Okay, let's do another example. Okay, let's consider the clamped beam with a spring. So we have something like this. Spring here. And let's apply a force in the same point F. This is X, 5. Mr. Poveda, is this determinate or indeterminate beam case? Mr. Poveda? Pardon, Miss Poveda, pardon, I'm sorry. Miss Poveda, is it determinate or indeterminate?
I think it's determinate.
How many reactions do you have? How many reactions do you have?
Five.
I did that for.
Now, just a second, please. I'm asking somebody. Otherwise, we will get. Miss Kimi, Mr. Kimi. Is this determinate or indeterminate?
The determination.
Determinate. Okay. How many reactions do you have?
5.
But if you have 5, that would be indeterminate. Come on. Mr. Fuertes, how many reactions do we need to determine in this case? How many reactions? Let's call this point A, and this called point B. Miss Jimenez, how many reactions do we have in this case? Miss Jimenez.
I think 4.
4. Okay, tell me, what are those?
RA,
Are A,
the moment in A, RA, sorry.
and then what?
Reaction in B and K.
Okay, so that's from the spring, okay, and then what? That's 3. You said 4.
And the K.
No, K is a come on. K is the
Force.
constant of the spring.
Yes.
Mr. Carranza, is that all, or you need something else? Do you have another reaction here, Mr. Carranza?
Yes, doctor. Good morning. The force.
Come on, the force is something that we know. This is known. This is data. This is an external force that I apply. Mr. Villalba, is there anything else that any other reaction that we need to include? Mr. Villalba, I cannot hear you. No?
There are no more reactions.
No more reactions. So that's 3. So the conclusion is that it is indeterminate, because we can handle only 2. So we have to solve the equation E I sub C B comma 1, 2, 3, 4 is equal to P of X. This is inside the domain. Boundary conditions. On X equal to 0, I'm not going to repeat it. It's going to be V is 0 and the slope is 0. On the right end, Mr. Dominguez, what's the bending moment on the right end?
0.
Yes, yes. So we are only. So M sub Z is 0. So that means that the second derivative at L is 0. How about the shear force, people? Well, the shear force is a problem, right? Now, the thing is this, on the right end, this is the right end, we have this force, which is equal to F. Now, what did we say? We said that if we have a displacement V, in this case, V at L, that's positive. The force from the spring will be downwards, right? So what we have is this force with value of K times B of L. In this case, the two add each other. Now, if we make a cut here, very close to the end, on this cut, the shear force, the positive shear force points upward or downwards. Ms. Avilés, shear force here, downward, yes. Remember, we do what that is. When we do not know something, we assume it as positive. That's it. So we have that minus VRL minus F minus K VRL is equal to 0. So the shear force, the negative shear force, that's the boundary condition, is equal to F plus K VRL. Minus V, it is equal to EI sub C. So here I have a boundary condition that's a third derivative of the function. Here I have the second derivative. I have a value of the function, a value of the slope. Translation, rotation. Here, this is translation, force, and have a value of the moment, rotation. So this is a consistent system, and we could solve it if we are careful with the deduction of the constants. Finally, Ms. Valdez, what's P of X in this case? What's P of X, Ms. Valdez? Huh? What do we have inside? Inside the domain, yes. What do we have here?
The force in the end.
No, you look, listen to yourself. The force at the end, but the end is boundary. So I know that you feel afraid, but say it. What is P of X? Mr. Vasquez, Kevin Vasquez, what's P of X?
P of X is gonna be I in parentheses delta minus 0.
Yeah, but what's the force that you have? What force do you have inside the domain?
No. We don't have any forces. It's gonna be 0.
So exactly. Now, don't worry, because here, the boundary condition on shear force, that includes a non-homogeneous term. Don't worry. But right now, there is no force. Why not? Because the external forces, these forces, were included in the boundary condition. So you don't have to repeat them. Now we proceed. So EI sub C V comma 1, 2, 3, 4 is equal to 0. We can integrate and
Doctor,
we can say, yep.
And what about the weight of the beam?
In this case, I'm not considering, but yeah, if you would include it, yes, I would put it in here. But in this case, it's not being considered.
Okay. Okay.
Okay, now, what happens with C and D, people? Mr. Ramirez, what the concept of integration C and D? C and D. C and D. Mr. Cedeño, Axel Cedeño, what happens with C and D?
Both of them are 0, I think.
Why?
Because when we replace the slope and the deflection, it turns to be 0 because of the first and second boundary condition.
Yes, exactly. So they both are 0 because boundary condition at 0. So we have to worry only about A and B. Now, for this, I have this boundary condition and this boundary condition. So we said EI sub C, B comma 1, 2, 3, evaluated at L. So it's going to be equal to A, and it's equal to, here it is, F plus K, B, and L. So that's one equation. And the other is this one here, the bending moment, and it's equal to A times L plus B, and that's equal to 0. Now, here I have V at L. Find this value, we need to integrate this equation 2 more times. So from here, we said EI sub C of V of X, integrate these 2 more times. So it's going to be to the 6 plus Bx squared over 2. C and D are 0. So we can say that I sub C via L is equal to A L cubed 6 plus VRL is going to be 1 over EI sub C. So now we can replace this here. So here I have an expression for A and B. Here I have an expression for A and B, so I could replace this into here, and we can solve. I'm going to give you my solution. My suggestion is please check in your house just in case. So A is going to be equal to F divided by 1 plus K L cubed over EI sub C. Please, at home, check. Everybody, tell me what are the units of these terms? Units of that term, everybody. What are the units of that term?
This is a dimensional.
Dimensional, yes. You did it, or you just assume? They have to be non-dimensional, right? Because it's combined to 1. This is non-dimensional, but it's a good idea that you check it. Okay, so it's going to be F over L for K. This is L cubed. This is F over L squared for E, and this is length to the 4 for the inertia. Got 3 and 2, that's 5. I have 4 and 1, that's 5. F and F, that's non-dimensional. So this is non-dimensional, this is non-dimensional, this is F, and this is shear force F. Okay, now, any questions so far? Any questions, people? Any questions in the process? Now, okay. What would happen? What would happen if K would be very large? See, the stiffness of the spring would be very large. What do you think would happen? If the spring would have a very strong, would be very strong, very large K, what would happen in that case? Miss Jurado, Miss Jurado, what do you think? What would happen in this case? If the spring would be very large, it's a very strong spring, what do you think would happen?
Maybe the force will be 0.
What force?
Um,
Can you imagine? Can't you imagine the problem? See, you have this is for everybody, okay? You have a beam clamped here, they have a spring on the right end. But now, this spring is very strong, and I am applying a force right here. What will be the situation? Mr. Villalba, what do you say?
It's like this side is clamped too.
Not as a clamped, but
the situation is similar in this case.
No. Because this point can rotate.
It's gonna be in equilibrium, maybe.
Always is in equilibrium. The system is all the time is in equilibrium. But more than that, if the spring is very strong, this will not deform.
The displacement is equal to 0.
I think if the spring could be simply supported.
Yeah, in that case, what happened at the end?
The deflection is 0. If
Okay,
the
but
K-
eventually, see what will happen is that, let me write here if I can find my pointer. So if K is very large, this would be something like this. How much would be the reaction here?
0.
Exactly. Make sense? Yes. This support is taking all the force. Now you see here, if K is very large, it's in the denominator. F over something which is very large will give you 0. So A tends to 0. Makes sense. The other case, what happens if we had no K, it's no spring? Or very soft. What would happen?
Would be like free.
It's like a free hand, yes. So that's something like this. What would be the reaction here?
F.
Force.
So this is 0, A is equal to F, that's a reaction, makes sense. Okay, in this case, this is F. This is F, and there's nothing here. Always, we are trying to check our results. See, what happens if I take this to the limit? And if the answer makes some sense, yes, it's a way to check our results. Okay, people, how are we doing with the homework, the assignment? Have you started the assignment? Let me ask somebody in Miss Acuña, Natasha Acuña.
Good morning, doctor.
Tell me.
I'll start the homework.
You are going to? Good.
Yes.
Or you already started?
No.
Okay, so you have no problem so far. Okay. Mr. Kimi, Mr. Elvis Kimi, do you have you started the homework? Mr. Kimi?
Today, doctor.
Good. Miss Poveda, have you started the homework, Miss Poveda?
Good morning, doctor. Yes.
Do you have any problems so far?
Not yet.
Not yet. Okay, good. Mr. Sawai, have you started the homework? Sawai?
Doctor,
Yep.
Not yet, doctor.
I have a
Okay.
question.
Yeah, go on.
I did the 5 exercise of the homework, and
Not yet, doctor.
Just a second, please. There's somebody else speaking
yes,
right now.
and
Go on.
I got the answer,
Uh-huh.
but I think that if I compare my graphics with a software, for example, that calculate the graphic of shear force and bending moment, I obtain the negative of the shear force graphic
Okay.
for the assumption that we do.
Yeah.
And I obtain the when I compare with the software, I obtain the graphic of the shear force and equal, and the graphic of the moment different. So the graphic of the moment is the negative, and the shear force is equal to the software. So I am confused.
No. The problem is this. Sign convention. Okay. For example, when we work with a single book, they use a different sign convention. Okay, that's all. Okay. The recommendation here is that if you want to check completely, what you have to do is look it up in the manual of the program. Okay, they have to specify the sign convention that they're using. It's probably different than the one that we are using. For example, at the end, I just completed the class notes. Today, I'm going to make copies. For example, the classification societies, we have to be careful because this is at the end of the semester, of the ship classification society. When they use they have a figure like this. Maybe you have seen it in the classification rules. And they say, here, the shear force is positive like this. And the bending moment is positive like this. So they coincide with us in shear force. They do not coincide with us in bending moment. So that's all. I would say that, yeah, if you want, look it up in the manual of the program. And they have to specify the sign convention that they're using. Okay, that's all. That's not a big problem. Please, for the calculation of the inertia, when you have inclined rectangles like this, okay, you can say that I have 1, 2, 3, and 4 elements. Yeah, this is 1, this is 2, this is 3, and this is 4. Okay, look in the appendix, Singer's book. okay? And what they have is, for example, if they have a figure like this, okay? And they have this figure, you could specify two axes. So for example, this would be X prime, Y prime, Y prime. Let me change color. And they have another axis, reference system. For example, let's say, okay, and there is an angle between these two reference systems. Okay, and they can relate the inertia of one of the systems. Okay, for example, they can calculate, for example, IXX prime prime and IYY. See, they calculate the inertia of this rectangle with respect to this axis, and also the inertia with respect to this angle, this axis. And then they, using theta, this angle, they can calculate IXX and IYY. So you have to review it in singles. And at the end, please check when theta is 0 or theta is 90, okay? You have this, apply a value of theta. If this is 0, then this one here should be equal to this one here. When this is 90, they should be equal to the other one. This has to be equal to this one. So this, in this way, you can check your results. Mr. Fuertes, have you started the homework, Mr. Fuertes?
No, no, doctor.
When are you planning to start the homework? It's up to you. I mean, if you don't want to do the homework, that's fine. But you should, you should know that if you have problems, I would like to help you. Mr. Carranza, do you have a question?
Yes, doctor. I have the question. In the problem 3, what would be the way of the propeller considered in the problem on the experimental situation?
Okay. I thought I include it.
No.
I'll check it up. It's not. I think it's.
No.
I think it's 2.3, but I'll check it up. But I think it's 2.3. It's 2.3. Isaac, can you help me? Isaac, are you there?
I check this value.
I think it's 2.3, but I'm not sure.
Doctor, I have a concern. I applied a force in this force, the 2.3, at the third task. So, but I include at the first for compare the experimental way. I did the moment considering the P of X like a weight of the axis, and then I didn't consider this way. But when I do the figure, the graph, the experimental graph is similar with the axis when I don't consider the weight of the axis.
You have to be patient, okay? Because experiments are good. I like it, but remember, they are not absolute. There are so many details that we cannot consider. Yes, if we are close, I would be happy. That's all what I can say.
Doctor,
Because-
the value, the weight of the propeller is 2.2 kilograms.
Something else before we leave, okay? If we have the shaft here, we have the strain gauge here, okay? The strain gauge registered epsilon x, okay? And that's because here we have a bending moment at x, okay? Now, if this is in bending, okay, epsilon x is equal, remember, sigma x over E, and this is equal to minus the bending moment times Z times Y, I'm sorry, over inertia divided by E. Okay? Now, if I go analyze this point here, okay, for this point here, Y, it would be equal to plus D over 2. And if I analyze here, Y is going to be minus D over 2. Okay? What we give you is the value of this strain when the strain gauge is up, then when the strain is in this position, in this position, and in this position. Okay? So if you have the value here and the value when the strain gauge is down here, you know that the difference between them is just a sign, right? Because here is positive, here is negative. Okay, and you know this and you know that. So we can say that E at the top minus E at the bottom. So in this case, minus MC is constant, E I sub C. Now, when it's at the top, this is D over 2. And when it's at the bottom, we are doing a negative. It's going to be minus D over 2. Okay, so this and that value, these are values that we give you. D, of course, is the diameter, Young modulus, inertia. And from here, you can calculate MC. So what you have to do is, this is the position for each one of them. So we start here, and then we rotate 90. So we go to 90, we change sign, we change value. Then we go to 180, would be when this is done here. And then we return. So this value is this one here. And this value and that one should be equal, is corresponding to this one. I'm sorry, this value is this one. I'm sorry, it's in the top. So this value is this one. And this value is this one. If you repeat this, of course, you are not going to have the same value. So we have to average and do something like that. So we know everything except the bending moment. And from there, with careful handling of units, you obtain the value that we're looking for. And then you compare with the theory. Okay? Don't forget, we have office hours. Isaac and myself were available. If you have questions, send an email to us and I will try to answer as soon as possible. Okay, people? Please, tomorrow, Wednesday, I will send some information for you to prepare the class on Thursday. You have to come to class reviewing the material, reviewing the material. Okay? See you. Bye-bye now.
Bye, doctor.
Thank you.
Thank you, doctor.
Thank you. Bye.
Hey, doctor.
Doctor.
You have to stop recording.